My name is Meghan Chandarana, in case you all don't already know me. I'm a PhD student at Carnegie Mellon, and this year is my first year as a Pathways intern, but this is my fourth summer here at Langley. And today I will be discussing my work on mission planning interfaces for robot swarms. So this is a quick outline of the presentation. I'm going to walk you guys through some motivation for the work that I do. I'm going to talk about what we call dynamic vehicle routing framework, which I use to kind of infer some of the policies we use for the work. I'm going to talk about the model that we have developed to help us do some prediction with these swarm missions. And then I'll talk about multi-agent mission planning as it stands now and how we can use this model to help leverage the capabilities and improve the planning that we do. And then I will walk you through a user study that we did to kind of assess the planning tool that we developed. And then I'll kind of switch gears a little bit and talk about another aspect of these missions where we kind of look at different behaviors we can do to actually accomplish the things we want to in these missions. And then I'll end with a conclusion and some future work. So in these robot swarm missions, we think about applications that I like to call swarm search and service missions. And these missions require a swarm to simultaneously search an area and service jobs as they appear. So these jobs can be one of multiple types. They can be things like people who need help because they have been lost in the wilderness. There can be fires that you need to put out. There can be a lost dog that you need to locate, basically. And these jobs arrive to our system, we assume, when they are sensed by our vehicle. So all we know ahead of time is how many we expect to see, but not necessarily where they're going to be. But we do know, if we do see a job of a particular type, how many vehicles would be needed to service those jobs, and for how long those vehicles would be needed. So what we say is that once a job is sensed, we allocate the required number of vehicles for a certain amount of time that we know, and then once those vehicles have completed the job, they rejoin the swarm for reallocation elsewhere. And in some cases, if too many jobs arrive at the same time, we may not have enough vehicles currently left in the swarm to be able to handle that new job. And these jobs are considered dropped. So for example, over here, you can see a couple jobs have arrived simultaneously here. And what ends up happening is we don't have enough vehicles. So maybe that job needed 5 vehicles to service it, but we only had 4. So we assume that we can't service it and it's dropped. And what we want to do is allow our human operator to predefine the size of their swarm such that they're able to handle these expected workloads without having these drop jobs, because these can lead to negative consequences like people not being helped if they need help, right? So what we do is we leverage something called the dynamic vehicle routing framework, and this framework allows us to think about things in more dynamic ways, like the title says. So instead of thinking about us knowing where jobs are ahead of time, like they do in static vehicle routing, we assume that jobs can arrive during execution. And what we do instead of traditional static vehicle routing is, instead of defining explicit vehicle paths, we instead define general policies. So if we see a vehicle, maybe we have a policy for determining which vehicle or which group of vehicles would be sent to actually accomplish that servicing. And by doing this, we allow ourselves to use something called algorithmic queuing theory, which allows us to evaluate our systems at steady state and gives us kind of a nice way of determining some prediction metrics, basically. And we assume our jobs are uniformly and randomly distributed in the environment. And another part of this DVR problem is the DVR problem with time constraints. And this time constraints problem basically is stated as such. We want to find the minimum number of vehicles needed to ensure that the steady state probability of our system is such that a certain percentage of jobs is successfully completed. And the way that we kind of think about this and do this in our models, we think of the converse problem, which is, instead of thinking about what we need to do to have a certain probability of success, we think about reducing our probability of failure. So instead we think about how many vehicles are needed such that we have lower than a desired amount of failure, or dropped jobs in this case. So our model takes advantage of queuing theory, like I said, and we leverage what is called an MMKK system. In this system, we assume that the jobs arrive according to our Poisson arrival rate, which means that they're independent of each other. One arrival is not dependent on another arrival. We just know that they arrive and they're uniform. The arrival is uniform and randomly distributed in the environment. And we have different jobs of different types. So we call these, we can think of a type I job requiring I vehicles simultaneously to be serviced. And we have a certain number of servers. So in our case, the servers are the vehicles in our swarm. So think about like a bank teller where like customers have to wait in line to be serviced. Instead, we have a swarm with vehicles that are the tellers, and they can be utilized to service the jobs, basically. And each job has a service time that is exponentially distributed. And in this case, because we're looking at when the system will fail, we assume that there is no queue, meaning if there are not enough vehicles when the jobs arrive, you can't help them, which is terrible, right? Like, we don't want that to happen. But that allows us to basically build really nice models. I'm going to skip all the math in this presentation. If you guys have questions, we can go over it at the end. So what we do is we build this model based on a simple grid world example. So think of a world that looks like this, where maybe we start, here on the bottom, and we travel with some lawnmower pattern through the environment, and we have jobs of different types. So here we have 3 different types. We have the purple ones, the green ones, and the yellow ones. And our job is to search the entire area and service the jobs as they arrive. And maybe we have, each job requires this many vehicles each for this amount of time. And we know ahead of time how many of each type there are. And that's what the bottom job configurations are. So in these 2 configurations, the first one has an equal number of jobs each, and the second one has an uneven number. And if you use our model, you can derive the relationship between the starting number of vehicles in our swarm with the expected number of drop jobs you would see in the environment. What's really nice is we get this exponentially decaying curve, and so as you increase the number of vehicles in your swarm, you're able to handle more and more of the jobs. Which makes sense, right? That's intuitive to us, and that's great that our model is able to capture that kind of relationship. So if we evaluate this model with both of those cases, we get the following results. So what we did is we ran 500 simulations for each of the cases with both a fixed service rate and an exponentially distributed service rate. If you remember, we assumed for our model that the service rates were exponentially distributed, but we wanted to see how it would do for fixed service rates anyway, which is kind of unrealistic. But we did it anyway. And so it's kind of like, you can think of it sort of as like a Monte Carlo simulation that we really did. And you can see that our model, shown here in these black dashed lines, does a pretty good job of capturing the actual behavior of a system of this type. So we're pretty happy with the way that we've built this model. And so the next step is, great, we've built this model that can capture the complex dynamics of the system. What can we do with it? And one of the things that we're interested in doing is using it as a planning tool aid. So can we give these relationships to a human operator who is tasked with determining the starting swarm size and better prepare them for making these decisions? And if we really think about the way that mission planning is done traditionally right now, what they do is they use typically things called ecological interfaces. And these interfaces, usually the control actions are based on visually perceived data. So think about abstracting away the layers of what each individual vehicle is doing, and maybe you have like some like group like graphic that you show instead of individual vehicles, and this kind of allows us to simplify what the swarm vehicles are doing, but it also makes it easier for a human operator to understand what they're doing. And excuse me, this work was derived from ecological visual perception, and it originally focused on allowing people to look at process systems. So think about nuclear power generation and petrochemical refinement. And it's later been extended to these multi-robot control interfaces. And by using these, what designers of these interfaces hope is that users have an increased, can use the increased transparency to make more complicated decisions by allowing this abstraction to happen, basically. Another way that they run these missions right now is that they do manual mission planning. So they maybe create a custom map for the mission, and they put manually in the system maybe the area of interest, the targets that you're interested in looking at, and then they go in and they manually prescribe the individual paths that the vehicles would take from point to point. So instead of thinking about policies, they're prescribing explicit paths, right? But the nice thing about these systems is that you abstract away the controllers required to actually run the missions, so you're not making them think about vehicle dynamics, which is nice. So instead of doing it manually, what people have thought about is looking at autonomous planning frameworks. But ultimately, what this boils down to is maybe you're using one of 3 common planning frameworks, maybe you're using a Markov decision process, or some game theoretic approach, or maybe some integer programming approach. But basically what it boils down to is the algorithm still prescribing individual vehicle paths instead of general policies and general behaviors of what the vehicle should do, which is really hard for a human operator to understand fundamentally if they are not a roboticist and are well versed in these algorithm theories, right? So let me just summarize some current limitations. So the first, like I mentioned, is that a lot of these frameworks explicitly describe vehicle paths. And in order to do this, they make use of multi-agent planning and multi-agent task allocation algorithms. But they require that you know the locations of your tasks ahead of time, which we don't necessarily know. And they assume, in order to make these calculations, some predetermined swarm size, which we may not know. What we're trying to allow our operator to do is to determine what that swarm size could be. And typically what they do is they choose just like the maximum number of vehicles that are allowed. So if they have 20 vehicles, maybe they allocate all 20 vehicles and they see what the algorithm gives them. And this may work a lot of the time, but in some cases, it could be that you have 20 vehicles, but maybe you only need 15, and you can save those extra 5 for changing out batteries, which is kind of what we want to take advantage of. So what we did is we gave this model to human operators, and we conducted a user study where we wanted to see if this additional model actually helped our operators. So their task was to specify the swarm size such that the total cost was minimized. And I'll talk about this cost in a second. We had 20 subjects. The 10 subjects were in our control group, and 10 subjects were in the experimental group, which means that they had use of this additional planning tool. And we did 10 trials, so 10 different missions per subject, and each trial had 3 job types. And there were cost values associated with the vehicles that you allocate. So for every vehicle you added to the swarm, there was a cost. So they couldn't just like infinitely, allocate vehicles. And we also penalized them for missed jobs. So if the swarm came to a job and didn't have enough vehicles, we penalized them for that because we obviously want to reduce that. And we looked at missed area. The purpose of these tasks is to simultaneously search and service. So if they ran out of vehicles, we cared about that, right? We wanted to keep searching the area, and so we penalized them for any missed area. So this is what the interfaces look like. The left one is the experimental group where they had the model. So this model here is similar to the graphs I've shown you before. And this model was explicitly given for the job types that were in this trial. So every trial had a different set of these job type parameters. And these job type parameters included how many of each type we expected to see in the environment, how long it would take to service a job of that type, and how many vehicles from a swarm were required to service that job. And they additionally had this model which corresponded to those parameters, versus the people in the control group didn't have any additional information. All they had was the information that was fed into the model, essentially. And what they did is they used the information that they were given to pick a swarm size. And what we showed them afterwards was kind of some feedback on what a mission of that type would look like given a swarm size that they chose. So the pink dot is the swarm. It'll play again. And the different colors represent each of the job types. Red indicated to the operator that they ran out of vehicles and they couldn't service that job, and so it was dropped. So you see the pink. And black was covered area, white was uncovered area, and gray was they didn't have any vehicles to service that area, and so they missed that area. So we showed them this as visual feedback just to see if maybe there would be some learning effect. Turns out there wasn't a learning effect because the parameters were different enough. So these are our results. So on the left we see that the experimental group was able to choose a consistently lower swarm size than the control group and reduce their total cost still. So they still had a lower cost even though their swarm size was smaller, which is great, which is what we want. The experimental group also was able to figure out a technique or a strategy for basically almost eliminating the total missed area. But by doing that, they actually found a strategy that caused them to have an increase in the number of drop jobs. So basically, this kind of plays out in this plot where we see basically that this experimental group basically eliminated this missed area, but still, whereas the control group didn't. And again, across the trials, we see the experimental group increased the number of drop jobs versus the control group basically kept them steady. And what they actually figured out is that the way that I picked my cost values, it just so happened that the cost of additional vehicles was about the same as a dropped job. As a dropped job. And so they were okay with decreasing the number of vehicles and only having maybe one extra drop job. But by doing that, they increased the number of drop jobs, even though we asked them to reduce the number of drop jobs. And they also figured out that if they left a certain number of vehicles in the swarm, if they picked an odd number of vehicles, they were able to always ensure that there were vehicles left in the swarm and that they were constantly covering area, which is interesting because it's just basically from the cost values we gave them. So they basically gamed the system, right, which is interesting, which is not what we wanted to see, but the point is that they were able to do this more effectively than people who didn't have the interface. So we're really happy with this user study. So the next thing that I'm going to talk about is switching gears a little bit, which is now that we've allowed our human operators methods for planning these missions, how do we actually execute these missions? So one of the things that's necessary for our vehicles to do in order to run these swarm search and service missions is the ability to deploy the subswarm team and then allow them to come back into the swarm once they're done servicing whatever job. So the way that we do this is we have a decentralized strategy, which I'll walk you through the steps. So the first step that we do is this is our job site here. And what we do is we construct a hop optimal spanning tree, meaning we ensure that this frontier node, which is the closest one to the job site, is the root node of the tree, and that the connection of each robot, the number of hops they are away from this frontier node, is the minimum number that they can possibly be away from the tree. So there's kind of this rainbow representation of the different levels of hops. So this is 1 hop, this green one is 2 hops, and so on and so forth. And we first construct this tree. And then what we do is we find the leaf node in our tree to a given depth. So this is our frontier node, and let's say that we are 2 hops away. Maybe this, around here, one of these robots would be a tail robot. And by doing this, we're able to push the vehicles that are between the frontier node and that tail robot forward so that no other robot in the swarm has to move. But what this does is that it creates this hole here. And what we do is we kind of figure out which robots can be pushed forward to fill in this hole. So the reason that we do this and cause the hole versus actually just planning a path directly from the frontier node all the way to back here is that when you have multiple job sites that you're trying to service simultaneously, this can cause confusion in the swarm for deciding who needs to move forward when. So maybe one robot will be chosen to move towards two different job sites. And by allowing ourselves to create these holes, we kind of eliminate the possibility of those robots being chosen for two job sites. And then it's much easier for us to figure out later how to fill in the hole rather than having that conflict, basically. So we basically find the robots that would be required to fill in the hole, and then we fill it in over here. And in that way, what we're doing is we're moving the minimum number of vehicles needed to actually move towards our job site without having to move any of the other vehicles, which is really nice. And then what we do is we keep moving towards the job site, and when the frontier node or the first robot is within range of the job site, we form our subswarm team. So it looks like this over here. And then once they've all serviced the job, we have a way to kind of rejoin them with the swarm. And the way that we do this is we define what we call virtual frontier nodes. So they're virtual positions in front of the swarm on the opposite side from the job site, and we kind of push a line of robots from the job site back into the swarm. And so again, we're only moving one line of robots instead of most of the robots. So this is a comparison of our method as compared to a full swarm moving, where every robot would have to move to the job site and then come back. So you can see them coming to the job site, forming the subswarm, and then moving back into the swarm, all the while maintaining connectivity, which is what we care about. And then basically we've tasked them with going to a goal location up here. So they use the virtual frontier node method to move towards the goal site also. I'm going to skip forward because this video was not sped up. Okay, so this is the full swarm method. So this is, if we just use that virtual frontier node method basically the whole time, we would have to move way more robots out of the swarm into the job site area and then back before we could actually move towards the goal. So this is that method, that subswarm method on our piglet little rovers that we have. So you can see them doing the mission where they have found a job site and they break off and create that subswarm team. This is our simulation environment, which we're able to, in real time, monitor what's happening. We can also save the information, play it back later if we want to. Or we can even run algorithm evaluations in the sim environment if we wanted to. And you can see them creating the subswarm team right here. This is the last robot that's coming into the subswarm team. And then afterwards, they rejoin, again, only one chain of robots moving at a time. And we also had different LED lights here that you can see which show the different modes. So that was from yellow to blue, which indicates the vehicles that were outside the swarm are rejoining back into the swarm. And then they continue on and do the rest of their mission. So here where they're doing the rest of the lawnmower pattern in the mission that we have given them. Okay, so what's the comparison with the full swarm method? What we can do now as state of the art compared to our method. So our method, shown here in blue, as the swarm size increases, we see that our method consistently requires fewer messages to be sent among the robots, which is really nice. That, reduces the strain that we have on our networks. It also consistently over here requires that the less number of robots move. So a total distance traveled by the swarm is reduced in our method versus the full swarm method. And we also see that as the percentage of robots required to join the subswarm increases here, that the average number of messages per robot sent actually decreases in this single job site case, which is really nice. This is what would happen in a multiple job site case. The same thing would happen where we, instead of going to one job site, we can simultaneously allow those jobs to be serviced. Versus if we were doing a full swarm method, we would have to individually go to each job site, re-enter the swarm, and then go back to the other job sites, which would take significantly longer. And here again, it's moving towards the goal site that we've given it. So if we do a comparison of the number of job sites that we want to simultaneously send our robots to versus the total distance traveled by the swarm, we see here that our method way outperforms the full swarm method. And we also see here, this is like the total distance traveled for both of them, basically. And you can see there's a huge difference. So I just want to conclude basically with what I've shown you today. So the work that we've done has allowed us to develop a prediction model for the relationship between a swarm size and the number of drop jobs that will be expected in these types of missions. We were able to run a user study where subjects with the planning tool had a better performance than those who didn't have the planning tool. The experimental group was able to assign fewer vehicles using this planning tool, having 7 times less missed area and 50% less costs than their counterparts. They were able to effectively use this planning tool as a baseline when they made these decisions. And we saw an effect actually across the trials for the swarm size, the drop jobs, and the total cost. And we also have developed a decentralized method for the sub-swarm break-off and rejoin, where the method requires less messages and less travel distance for the swarm. It scales linearly, and less messages are sent per robot as the ratio of sub-swarm robots to robots in the swarm increases. And robots travel about 4.13 times less distance than the full swarm method. And for future work, what we're thinking about doing is exploring the effect of these cost values. So I mentioned that the way that I picked the cost values kind of affected the strategy that people had. It will be interesting to see in the future how changing this ratio of cost values will change the strategy and also the performance of these users. We also want to look at additional model modifications, basically. So can we model more complex missions? So we're looking at things like how can we model different formations that the swarm does? How can we model, maybe we have information about a general area that jobs could be in. Can we leverage that information to look at those bias regions and infer and improve our prediction? And then can we also look at the real sensors and look at the real probabilities of detections, basically? And then we also want to look at evaluating the efficacy of these models for higher dimensional trade-offs and look at things like heterogeneous vehicles. And that's it. Thank you for listening. From moving into the hole. So you will still have that conflict, but it's much easier to deal with the conflict after the vehicles have moved out of the swarm than if you're trying to determine which tasks they need to go to. Versus when your problem is kind of localized to the swarm vehicles themselves, it's much easier to kind of say, hey, I've already been chosen, let me nominate a neighbor robot instead. It's much easier to do that than for the vehicles themselves to figure out which job to go to.
Because you have more neighbors if you're in the middle.
Exactly.
Talk a little bit more about your human subjects gaming the system.
Mm-hmm.
So you talked about going back and maybe looking at cost functions.
Mm-hmm.
So that makes a lot of sense. Did your human subjects, did they have a meta goal or a mission goal other than don't drop jobs? I mean, were there things about priorities or,
Mm-hmm.
and I'm wondering what are your thoughts on if the humans had sort of these meta goals, how would that impact their ability to game the system?
So all we did was when we tasked the human operators was ask them to choose a swarm size such that fewer than some desired number of fewer than a desired number of drop jobs happen. So we told them like 5. Try and pick a swarm size such that 5 or fewer vehicles caused our system to fail. And we did this because that's how we picked the correct size, in order to do the comparison. And what this basically does is just give our operators a baseline for determining where along this curve they need to sit. So all we did is try and tell them where they should, kind of decide, what general range to be in. Other than that, we gave them no other requirements other than fewer than a desired number of jobs. Everything else is just things they were able to learn based on like what values we gave them and, what they thought their goal was, basically, right?